Hi, in the previous lectures, we talked about hydrostatic law that states that pressure increases with depth in a fluid, in a static fluid. Okay. Then we talked about manometry, which are pressure measuring devices whose operating principle is hydrostatic law. Then we have derived expressions for forces acting on a plane surface. Also, we have discussed based on force balance, how can we compute forces on curved surfaces. Okay. And in today's lecture, we are going to talk about buoyancy as well as stability of submerged and floating bodies. Okay. So let us start with the concept of buoyancy. Okay. So you know that when a body is partially or fully submerged in fluid, okay, if we have a body submerged within a fluid, it experiences a net outward force due to the surrounding fluid. Okay, it experiences a net upward force due to the surrounding fluid. Okay, and this phenomenon is called buoyancy, and the upward force is buoyancy force. Okay, and let us consider this is a fluid medium, okay, actually free surface. Okay, so when you know that if it is a inverted rectangle, then it denotes a free surface. The fluid is below this free surface, and we take a body immersed in the fluid. Okay, a body of arbitrary shape. This is immersed in the fluid. Okay, now let us consider a small element, okay, of cross section delta A. Okay, so the cross section is delta A. Okay, so you know that so this body experiences pressure P1 due to the surrounding fluid, and here it will be P2. Okay, and let us denote the distance from free surface of point 1 as h1, and let this be h2. Okay, so we can write that the net force on, so the buoyancy force on the element on the element, so let us denote this as delta FB. That would be integral P2 minus P1 times delta A, which is the cross section. Okay, so we are saying that the buoyancy force is a net upward force, so we have taken P2, which is acting upward, and P1, which is downward force. So the net buoyancy force on this differential element would be integral of P2 minus P1 integral delta A. Okay, now P2 and P1 from hydrostatic law can be expressed as, okay, rho g h2 minus h1 delta A. Okay, so this is using hydrostatic law. Okay, so delta FB would be rho g times h2 minus h1 delta A. Okay, so this integral will give you okay, so okay, so I have made a mistake in convention. Sorry, when we talk about buoyancy force on the element, this integral will not come. Okay, so sorry about that. So the total buoyancy force FB is actually delta FB. Okay, so that would be rho g times integral h2 minus h1 times delta A. Okay, so this integral will give you volume of the body. Volume of the body that is immersed in the fluid. Okay, so FB is rho g times the volume of the body. Okay, so that is the buoyancy force acting on the body that is partially or fully submerged in the flow field. Okay, this is nothing but the Archimedes principle. Okay, that says that the net buoyancy force is equal to the weight of the liquid displaced by the body. Okay, this is what it says. So the left hand side is the buoyancy force, the right hand side is rho g is volume of the fluid, and times volume is the weight of the liquid displaced by the body. Okay, so this can be represented as, the same body. Okay, if we draw the forces acting, okay, there will be two forces acting on the body. One is this buoyancy force FB, that acts as the point called CB. Let us say CB is the center of buoyancy. The point at which the buoyancy force act is called center of buoyancy. Okay, you can very easily guess that the center of buoyancy is equal to the centroid of the body. Okay, not center of gravity, centroid of the shape of the body. Okay, and another one, it's well known, the weight will act at the center of gravity. Okay, so there are two forces mainly acting on a body submerged or floating. One is the buoyancy force that acts at the center of buoyancy. Center of buoyancy is the same point as the centroid of the body, and the weight which acts at the center of gravity. Okay, so as you know from your high school physics, is that the buoyancy force, if it is equal to the weight of the solid, then the body will float. If it is less, the body will sink. Okay, all right. So now we had a brief discussion about the buoyancy. Let us move on to stability of submerged bodies. Okay, so again, let me draw the classical diagram. Whenever we discuss about stability, we draw this classical diagram, a ball, that is placed on this surface, and this one, and this one. Okay, by stability, what do we mean is that we give a small disturbance to the body, and as the effect of this after applying the disturbance, if the body comes back to its original equilibrium position, we say that it is stable. So you know that this is a stable equilibrium, because if I give a small disturbance to the body, it will displace here. Then after I leave leave it out, it will come back to its original position. Okay, so this is unstable. Okay, because you give a small displacement to the body, it is going to continuously go further away from the equilibrium position. Okay, this is neutrally stable. You give some disturbance to the body, it will move to a new position, and then it will neither come back nor move away from this position. This is another equilibrium position. Okay, so if the effect of disturbance dies out and the body comes back to its original position, we call that as a stable configuration. If the disturbance is amplified and the body moves away from the original equilibrium position, it is unstable. If the body finds another equilibrium position due to the disturbance, then we call the configuration as neutrally stable. Okay, so now we are going to talk about the stability of submerged bodies. Okay, a body that is completely immersed in a static fluid. Okay, so again there are corresponding to this, there are three configurations. Let me draw the free surface, a common one. So this denotes free surface. Okay, so case 1 is that the center of gravity is below the center of buoyancy. Okay, just we have seen center of gravity is the point at which the weight acts, and center of buoyancy is the point where the buoyancy force acts. Okay, so this is case 1. So let us consider an arbitrary shaped body. Okay, so in which we denote this as the center of buoyancy, where the buoyancy force acts, and then this is the weight. So this is the center of gravity where weight acts. Okay, so what I'm going to do is I'm going to apply a moment which results in tilting of this body. Okay, so what I'm giving is, so okay, I hope so that is supposed to be the same figure, but it is not exactly the same. So what I have done is I have applied a moment in this direction, okay, and tilted the body. Okay, so what would happen is that this center of buoyancy is here and the center of gravity is here. Okay, sorry, yeah, so now after this tilt, this body experiences a restoring couple in this direction. Okay, just to make it more precise, or for you to easy understanding, let me draw center of gravity and center of buoyancy on the same lines. Okay, so what we have done is we have taken a body that is initially in equilibrium. We applied a moment in this direction. As a result, the body tilts. Okay, so the center of buoyancy and the center of gravity will not change for a body completely submerged. So as a result, you can see that in this point the weight acts downwards. In the center of buoyancy, the buoyancy force acts upwards. As a result, it creates a couple in this direction, which will restore the body back to its original position. Okay, so applied moment, for example, in this case is clockwise. Is it clockwise? And the restoring couple is in anti-clockwise. Okay, as a result, the body comes back to its original position. Okay, so the applied moment and the restoring couple are in the opposite direction. Okay, so the body after giving a small tilt will come back to its original position. So this is stable equilibrium. Okay, so let us consider the next case where, okay, so the case 2 where CG is above the center of buoyancy. Okay, so again we have a body. Okay, so the center of gravity is above the center of buoyancy. Okay, again I am going to apply a moment. Sorry. So again I am going to apply a moment in this direction. As a result, the body tilts. Okay, so this is the applied moment. Now you see that the weight is here and center of buoyancy here. The moment as a result of the tilt, you can see the forces are arranged in such a way that the net couple is actually an overturning couple. Okay, so instead of bringing this body back to the equilibrium, the overturning couple will move it further away from this equilibrium. So this is unstable. Okay, so in this case the applied moment and restoring couple are in the opposite direction. Here they are in the same direction. Okay, we applied moment in the clockwise direction. The restoring couple, due to this arrangement, you can see that this is also in the clockwise direction. Okay, so the body moves further away from the equilibrium. Okay, the third case is a simple one. CG and center of buoyancy are at the same point. Okay, it's easy to guess. So this is FP and this is the weight. You apply some movement, the body will tilt. Okay, and FB, and this is the applied moment. So there is no restoring couple, so it neither comes back to its original configuration nor move away from the original equilibrium position. So this is neutrally stable. Okay, so to have a stable configuration, what we should, if we have a body submerged into the fluid flow. Okay, so to have stable configuration, the bottom of the body, should be heavier than the top. This should have more dense than the top, so that CG will be below center of buoyancy. Okay, this is the condition for stable equilibrium of a fully submerged body. Okay, we want CG to be below CB. This can be achieved by making bottom half of the body more dense than the top one. Okay, so let's stop here and we will discuss stability of floating body in the next video.